In this video, we're going to explore some of the consequences of Varignon's theorem. Now, this theorem is a very surprising one and a rather simple one to prove, and it states that if you start with any quadrilateral ABCD and you construct its midpoints EFGH and connect them to form a quadrilateral, that quadrilateral EFGH, shown here in red, is always a parallelogram. Now, dynamic geometry software like Web Sketchpad makes this very inviting to explore because we can, after making our construction, drag any of the four vertices of A, B, C, D. We can drag them even to very unusual positions like this one, and see that, try as we might, EFGH always seems to remain a parallelogram. Quite fascinating. Now we can prove this, and it involves constructing the diagonals of ABCD, so AC and BD, and using some very elementary geometry, we can show that FG is always parallel to BD, and EH is also parallel to BD. So therefore, these opposite sides of EFGH are parallel to each other. And we can do the same with the remaining two sides, EF and GH. But that's not really the goal of this video. We're going to look beyond the proof of the theorem and see what else we can do with it using Web Sketchpad. So, EFGH is always a parallelogram. Well, what kinds of parallelograms are there? We could have a parallelogram that happens to be a rectangle, or a parallelogram that's always a square, or perhaps one that has four equal sides and is a rhombus. So can we restrict the vertices of A, B, C, and D so that no matter how we drag them, this midpoint quadrilateral shown here in red is, for example, a rectangle? Well, if we want the red parallelogram to be a rectangle, then the diagonals AC and BD need to be perpendicular to each other. And I can approximate that here by dragging point D to keep BD perpendicular to AC, but I want to be able to ensure that it is always perpendicular to AC no matter how I drag it. I don't want to be careful about it, and I don't want to approximate these two segments being perpendicular. Well, with most dynamic geometry software, Desmos GeoGebra, you would have to build this construction from scratch to ensure that the two diagonals were perpendicular. But with Web Sketchpad and Mac Desktop Sketchpad, you don't have to. You can, in fact, do that after the case, having already built this. So let's see how that works. I want to construct a perpendicular to the diagonal AC. So I'll click on the perpendicular tool. I have a segment glowing. I'm going to attach that to AC. And now I am going to attach this point that's glowing to point B. So what have I done here? I have constructed this line, which I will make a different color. What should I make it? How about green? So I have, let's make that thicker while we're at it, so we can actually see it. Okay. I have constructed this green line that passes through point B and is perpendicular to AC. Well, if point D were to sit anywhere along this line, then our midpoint quadrilateral, the one shown in red, would be a rectangle. With other software, as I said, this would not be possible because D was not constructed to sit on the green line. But you may have noticed that when I moved D over the green line and point D were highlighted. And if I let go while they are highlighted and glowing, then, lo and behold, D is now attached to that green line. These two diagonals, AC and BD, are always perpendicular, and our parallelogram is now always a rectangle. All right, let's move on to the next case. What if we want our midpoint quadrilateral, shown in red, to be a rhombus? Well, in that case, we want the two diagonals BD and AC to be equal in length. So I am going to use the Circle by Center and Radius tool. I am going to construct a circle centered at B. So I will click to attach the glowing center of this circle to B. And I want the radius of this circle to be equal to AC. So I will tap to attach this glowing segment to AC. All right, so now if point D were to sit on this circle, then we would have two diagonals, AC and BD, that were equal in length. Well, I can do that. I can simply drag here and then let go. So now I have these two diagonals, AC and BD, that are equal in length. And no matter how I drag the four vertices, I always obtain a rhombus. Okay, now I want the midpoint quadrilateral to be a square. So I'm going to have to combine what I just did, those two previous ways of restricting point D, because I want these diagonals AC and BD to be both perpendicular to each other and equal in length. So to start with the perpendicular, I'll construct a perpendicular to diagonal AC passing through point B. Once again, why don't we change that to green and thick. Now I also, so D is going to sit somewhere on this line, but we need to make sure that BD is equal to AC. So I am going to now construct a circle centered at point A with radius, let's construct that at B with radius AC. So right there is the point that I'm looking for, where if I drag point D there, I will have BD equal to AC and the two diagonals perpendicular to each other. So I'll let go right there. And now I claim that this red quadrilateral is a square. And no matter how I drag these four vertices of A, B, C, D, I have not only a parallelogram, but a square. Now you can find this sketch that you can play with yourself on the Sign of the Times blog. There's a link to it right below this YouTube video. And I invite you to explore the other geometry-related posts on Sign of the Times.